In today we are studying lecture 10 about confidence interval. So let's just get into it. There are three sections here, as you can see on top of the lecture note: the estimation, confidence interval, and author confidence intervals. So this is the main topic about the confidence interval. But before we can understand what it means and why we need it, we need to talk about estimation first. But let's recap quickly of what we have learned so far. Last time, should be like last few lectures, we learned that we talk about normal distribution, a bit continuous distribution where the curve looks like this, a nice bell curve, symmetric. It has a lot of good properties. And this come into families. Like it's not just this single shape or single curve. Like sometimes you can shape it to the right. Sometimes you can make it taller and narrower, or you could maybe shift it to the left and make it wider and also lower. So that's a normal distribution. Yeah, but since there are too many shapes, too many different kinds, depending on two parameters, which are the average, the mu, and the standard deviation, sigma. So if you change these two values, the shape will change, right? And we denote that by this notation. So if you pick mu and you pick sigma, then you can plot a graph and use an app to help you compute lots of values. And then we focus on the standard one because that's easier to understand and the numbers look nicer. This is the special case when the average is 0, mu is 0, and also the standard deviation or sigma is 1. So we have that, right? And we talk about, how to compute areas, how to compute probabilities. Oh, I should also denote that. Like we still have the random variable. That's just some value that we don't know yet. I think about, if the curve or if the distribution is about human's height, then Z is, picking one person at random and measure their height. And that height of a person or of this group of people, like you follow this curve where, you are more likely to get people who has height around the average or the peak of this curve. And once we have this curve, like once we have distribution, then we can talk about what is the probability that the Z value or the person that we pick randomly have high greater than some value. Maybe let's say 145 centimeters or something. And that's gonna be, the area under the curve. And once we plot a graph, and once we identify where that value k is on that graph, then we can make a region, like make a line, straight line on that value k, and then shade or fill in the area to the left or to the right, depending on this symbol, whether it's greater than or less than. So that's what we have so far, and then we know how to compute this using both the app and both some properties about the curve, right? And also the inverse. Right? For instance, if let's say you have again students with various, let's say, score, and you want to find the point. You want to find the 80th percentile. Find the cutting point where 80% of the students have score below this point. And you can also use the same curve and also the same tool to find that cutting point where the ratio is or the probability is of that value. Right, that's the first one. There are lots of combinations, lots of new concepts. And then also that the Z table. Nowadays you can use any decent application on your phone or on laptop, on web browser, and that can be used to compute that. And I think we touched a little bit on some applications, like what this curve, or what all these things implies. It implies that the average of means is normally distributed. But that sounds weird, right? It's the average of the means. The average of means is like we take the means of the means. It seems redundant, but it's not. But if you recall the animation or the image about animals, or I think they are rabbits. Like if you take one rabbit and see how much it weighs, then you get some numbers. And if you take the top rabbit, maybe you get some random curves, right? But if you take a bunch of rabbits and weigh them all together, and then take the average, we don't take the sum of all the weight, we take the average. Right? Then that average will look very much like the normal distribution. And now this is something that we can use the app, we can use tools, or we can use your friends to help compute for that. So that's all we have so far about the normal distribution, and also the standard normal distribution. And today, and actually from now on, we're gonna dive into the basic application. This might feel weird because we only touched that topic for a week, and now we move into the application already. But the thing is, first, it's gonna be more complicated real quick. If you want to go into more details on how to apply those values and what kind of distributions there are, and it's gonna take some time to get through all of them. So that's one thing of why. And second, interestingly, these are all we need to know before we can apply them. It's enough to understand the concept about probability, about the normal distribution, the area, like what it means for the probability of some value to be, less than a certain point. Like that's all we need to use in the actual application. And so that's why we just skip through all of those things. I said, let's get right into it. And so first we are gonna use normal distribution, the curve that we just draw and study, to estimate things. What is estimation? Then of course we have a random variable, some number that we pick among a group or a population. Right? And we don't know that, we have no idea about that value, of course, because that's random. Like if we ask you to ask a person on street how old she is or he is or they are, right, then that's no way you can tell exactly. But if you ask you to estimate, right, then you might say, oh, maybe that person, the age of that person could be between, I don't know, 18 to 35, using some math or using some clever deduction. And this is what we are going to do first here about the estimation. But first, before we start estimating, let's recall why we have to do all these things. And because again, if I ask you to estimate an age of a random person on the street that you see, you can just think, oh, it's something between, I don't know, 20, 25. You can pick two random values. And that could be a fine estimation. And sometimes it's based on just your gut feeling. It's based on some information about the location. Like if I ask you to estimate age of a student in college, then of course you're gonna get some values between 18 and 25, maybe. Like given some information, you can narrow down the number. But that's not what we do here because we need some math to support that. And so, we go back a step. Like we show this. I think this is the third time we see this image. Like that, there are two branches of statistics. First, the descriptive statistics, like giving a set of data or giving a spreadsheet, like a big table. Like how can you make it look nice or make it more readable? Organize it so that it is easy to see what is outstanding or what is important. I mean, that's one thing. There are lots of tools you can use. You can just stay in using spreadsheet or Excel forever. You can do fine. And the other branch, which is what we are studying right now, is the inferential statistics. This is where we use some data, like, and make some prediction or make some estimation or make some some model on what it actually looks like in reality. Because this is just a limited set of data. Let's say you get that information for maybe 5 years, for instance. That's maybe yearly goals of your company. You may have 5 years worth of information, and you make some nice looking graph. Yeah, but then you can use that to both maybe estimate guess about the past and what it will look like, what it looked like in the past, and also about the future of how our company would be doing in maybe 5 years, 10 years, to get a better sense of what is actually going on there. Right, and the curve that we saw back then, like, is the normal distribution that we just studied last time. And given the information, we can make a nice curve, and based on that curve, or based on that graph, we can deduce or we can conclude something meaningful. And this is yeah, I think I showed that lecture 1 or 2 maybe, like that. If we talk about the whole process, like the big picture of what this course is about, like everything is condensed into this single image, like where we have the process of sampling in the first place, like maybe making a poll or just ask people or look at some group and take some samples and take a bunch of objects and measure them or weight them or do whatever you want to do with them. And then we use descriptive statistics to get a quick look on what we got. And then you can get some graphs to make it look nice, and we see something interesting to study further. And then we can use the center of the spread on the mode, find the mean, find the median, the 3 M's, and also find the spread, like standard deviation, variance, maybe the range, the MAD, mean absolute deviation, and there are lots of things you can find. But in practice, you can just do that. If once you have everything in spreadsheet, you can drag everything or maybe load an add-on. You get all of this information just by a single click. But what's more important is what we do next. And now we need to use statistical inference or inferential statistics. Or maybe I should flip that. Right? In combination with probability, and with the math that we just learned, like to achieve two objectives, which is what we are going to study next. Like first is to make some estimation, which is the content of this lecture, and then use that to perform hypothesis testing. To be toward the end of the course. Like, but eventually, and what is the most important part of all this process is to make a decision. And to use all this information to help us make a better decision. And that's the idea of what we have learned so far. And we are here. Like we are here. Like we learn all these things already. Maybe not that. Like all these things. And that's what we have so far. We are very close to the end, to completing this whole process. Right, but is it a rigorous process? In a sense that, okay, everything is proven, everything has some theories to back up. Right, but let's take a look at the next one. In reality, that's where the mistakes could come from. Most of the time, you get some sample. Maybe let's say you ask 5 people on the street, hey, do you like Bangkok? And they all say yes, 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 yes. Maybe one no. And then you make a decision or you make a conclusion. Oh, most people love Bangkok. That's what happens, right? You get a small collection or a small set of samples, and then you make a decision based on what you see at glance. And that's not what what you should do. If you need to make an important decision, that's not what you should do at all. But we are people, we are full of bias. You see what you want to see, and yeah, everything else is blur. So maybe that's the goal of the course, like to not make a shortcut and just jump right into the conclusion, but make sure that you look at them and then understand. Okay, they are just 5 people. 5 people doesn't represent anything, and so you shouldn't conclude anything based on the small size of 5 samples. Yeah, but a meme, like you to be rigorous, not to be academic, they would say you need to put a graph, 5 mean and variance, 5 confidence interval, test the hypothesis. Like there are steps you can take to make sure that you get the right number. But of course, instant decision making. Just go right through it. Maybe it's good or bad, I don't know. It's on you to judge or to see. But yeah, let's get back to sampling first, right? And also why we need to estimate. But this is an example of a very biased sampling, where we have this big bulk of people. Let's say the population, and there are 500,000. Of course, there are not that many dots, but suppose there are that many, and 90% of them are blue. And blue red, usually representing the political size in the US, but let's just think of them as just balls with colors. Like there are lots of blue balls. Like if you pick one at random, you should expect to see lots of blue balls as well, of course. Like, but sometimes maybe based on the process, or maybe you look at the bin, you look at the whole thing and pick what you want. Now you could get lots of red balls instead. And that's gonna be, give you a false impression of what are actually inside this big box of balls. And that's a problem. Like we don't want this to happen. Like that's bad. Like we want to discover the fact or discover what most people think or most people have. But sometimes we get some false impression or even like misleading information. So this is the process. Like we have some population that in fact we are not supposed to know that because there are too many people to ask. Like we don't know exactly. We could, but it's gonna take a lot of time and resources. Yes, so what we do is you could do is just take some more samples and see how many balls of each color there are. And this is the process of using just a small sample to estimate the whole population. is of course called the estimation. But before we move on, we have to discuss a little bit about the convention of how you could write these numbers, right? Because there are two numbers here. Right, on the left we have 90% or like 0.9, and on the right we have 30% or 0.3. And these are of course two different numbers. And they both represent the same concept, which is the ratio of the blue balls compared to the whole box or the whole population. Okay, so to make sure that we don't confuse ourselves which is which, like we create some new parameters or some new symbols. So first, a numerical measure of a population is called population parameter. So it's parameter, like some numbers, and we can that could vary, and we call that population because those are the numbers based on the whole population. And once you take a sample, maybe take 10, 20, 30, right? Then whatever you get from that small set of samples is called a sample parameter. So it's still a number, but just from the sample, like not from the whole population. And on the left, we have the symbols we use. Let's start from the right then. And what we actually do so far is what we have on the right, which is you are given a complete set of information. And you are asked to find the mean, the proportion, or the variance. And on the right is a population parameter. Mean is denoted as mu, and the variance, I think it's standard deviation. It's denoted as the sigma. And this is what we saw in the distribution notation. N of mu and sigma. Like suppose that we know that the what the actual mean or what the actual variance standard deviation is. And also we didn't use this a lot, but this is gonna be used sometimes in the future, which is a proportion. Maybe this is what we saw up here. Like what is the proportion of something and compare with the size of the whole thing. So these are the parameters that we use for the population. But once we take just a small bit of samples, we change the notation a little bit again to make sure that these two concepts are separate. And for the mean, instead of using mu to represent the whole population, we use x bar. And usually, like in textbooks, I will try to make sure that I denote that or also write it as the sample mean. Not just, just give you a random notation and expect you to know which one which is. I will try to make sure that I identify which whether it's a sample parameter or whether it's a population parameter. So we have an x bar for mean. And then we have S for variance and the P hat, the hat for the proportion or the ratio. And this, what we got from this, for the sample, we gonna use that to estimate the actual value behind the scene or the actual value that we didn't know or couldn't find out. And some note here that the population parameters are fixed, they are constant. Like this blue are always just that number. It doesn't change. Unless you ask for things that could change, like maybe height, weight, or age. But if you think about, just a small, maybe like a year, like within a year, like this number shouldn't change that much. Like why the sample could change based on one experiment to another. Maybe you ask for, you get a sample size of 10, ask 10 random students on campus this week. Then you get these 3 values. And then next week, you ask a new set of 10 students, and you're gonna get, of course, a different values, and then different parameters. So this could change from time to time, but not the blue one. And so let's take a look for a moment, like what to distinguish between these 2 values. So these are about, again, balls, because we talk about balls a lot. So why not talk about Pokeballs? Suppose you have a bag containing 30 master balls. So that's gonna be the good one, in case you haven't played this popular game yet. Like this, I should make it yellow. Then there's a good balls, good, expensive, and rare. But you only have 30 master balls in your bag and 70 normal balls. Because you are just a cheap trainer, you don't have all the money to afford that. And so you get some good ones, some normal ones in your bag. And maybe you know the content of the bag, maybe you don't. And maybe you pack the bag yourself, so you know. But let's suppose we are taking a look at this bag from the perspective of someone else. Maybe your friend take a look at your bag, and they want to say, oh, how many balls there are in the bag. And so you, or maybe your friend, take a sample of 10 balls without replacement. That's just a fancy word of saying that, oh, you take one and then you just leave it outside the bag and take another, leave it outside the bag until you have 10 balls outside the bag. No replacement. You don't put it back to the bag. And suppose you get 4 master balls. In this case, this is what you see on the right. Out of these 10 balls, 4 of them are master balls. And here there are 2 different numbers. The content of the actual content of the bag, and what you or your friend get from the bag. And there are 2 values here. Right? If we talk about proportion, like the ratio of the balls, and there are 2 proportions to talk about. We have to talk about the population parameter, or the population proportion, which we denote as a P, like the P on the right. And the simple one, maybe just a P hat, not the hat, but the hat, P hat. So there are 2 numbers, and here, like the number we have at first, like is the actual contents of the bag. Like we have everything, and this everything, like is the bag itself, which is the population. And what we get from the bag, like is the symbol. And so there are 2 values here. And to find those numbers, then you simply do the math. And so to find the proportion, or actually I should also say the proportion of master balls. Of proportion of master ball. And how likely it is that you're gonna pick a ball at random and get a master ball. Like for the bag itself, like there are 30 master balls. Like among the total of 100. Like so the population parameter is 0.3. You get about 30% chance to pick a ball at random and get a master ball. Right? But for this experiment, like for this specific set of sample, like the proportion that you see here is 4/10. You got to see 1, 2, 3, 4 master balls. So it's 0.4. Which, as you can see here, it is slightly higher than the actual population, which means you are a little bit luckier to get good balls out of this bag. Right, but of course, this is just to illustrate the concept of the difference between these 2. Right, but in reality, you're not gonna see that number at all. And so that's why we need to use some math to help us get a good number. So there's a concept here. Like given this, we can compute these two values. Like, but again, here, the in reality, like you get this p hat based on this is 10 power of the p hat on the sample parameter is 0.4. The question or the objective here is, can we use that 0.4 number that we got like to make some meaningful estimation on what the actual ratio or what the actual parameter p is? Yeah, because again, looking from like the perspective of your friend, they don't see how many balls are in the bag. They just see a bag with lots of balls. Right? And based on this one sample, can you or can they make some nice estimation? And again, like if you use no math at all, like based on this one, you may say, oh, it should be about 0.4. Of course, that's a rough estimation. Like with no, it's just a naive estimation. Right? But 0.4 itself, like the number itself, doesn't make sense, right? Because in fact, you would expect to to have some error. The number you got is 0.4, but in reality, it could be like slightly higher than 0.4. Let's say maybe it's 0.5, maybe, or it could be like about 0.3, like about 0.1 below the sample parameter. And so maybe this is a more natural way to estimate something, and to give a range or to give an interval of what you think the values could be. And because of course, if I get 0.4 here, like nobody is gonna estimate the actual population parameter to be 0.9, right? And that's why, because it's too far. Like we can see just looking at these numbers, like, oh, it's too far. And also, if 90% of the balls in this bag are master balls, then why would you get only like this small ratio? If almost all of the balls in the bag are master balls, then you would expect to see 9 or even like 8 master balls from this sample. But that's not what happened. And so we can rule out 0.9 really quick. And also maybe you can rule out 0. Of course, like 0 means there are no master balls in this bag at all. And if there are no master balls at all, then how could you pull 4 master balls out? That doesn't make sense. And so it would be, more intuitive and also more useful to give an estimation in terms of a range. Okay, we get 0.4, but we are pretty confident it's not going to be exactly 0.4. So it's going to be 0.4 plus something and 0.4 minus something. But the next question is, like, what are those plus or minus numbers? How can we know whether it's 0.4 plus or minus 0.1? Plus or minus some error? And the question is, how do we determine what that error is? That's what we're gonna do next. Okay, so that's the motivation here is that okay, suppose there are just 10 balls. We'll just make things easier. But again, you don't know how many of them are master balls. Right, then if you want to know the content of the whole bag, then there are several ways to do. First, you can just, pull everything out. Then you're gonna find the exact value of p, which is nice if you could afford to, pull everything out. But suppose you only pull 9 balls out. Maybe let's say this is what you got. You got some red. In this case, it's pink. And then we get some master balls. And then some misrace ball in the back. But this is what you have. then what would be your conclusion? What are the, if you ask what is the ratio or how many master balls there are there in the bag? And you will say, oh, since we see two and there's one missing or one mysterious ball that we didn't pull yet, and then the best we can do is we can say, oh, there must be two or three balls in the bag, two or three master balls in the bag. Or if you change that to the proportion, you could say, oh, it's about 0.2 or 0.3. If you leave a single ball in the bag, then the best you can do is, your estimation will be this, between these two numbers. And also, if you express that in terms of a range, you could say it's between 2 and 3, the close interval 2 and 3. In reality, it's not going to be like 2.5 or 2.4 because the number of balls are exact. Yeah, but this is the discrete example, so numbers are integers or numbers that you can list. But in reality, the numbers are the variables are continuous, and so you would expect to see a range. Yeah, but in this case, let's just use a range to make us familiar with the notation. Yeah, so your answer would be a range of some kind. If you talk about the number, could be 2 or 3. If you talk about the proportion, the 0.2 and 0.3. For instance, if you get 9 balls. But then let's say you don't have enough time to put all those balls. Maybe you only pull, not push but pull. Let's say you only pull 9 balls or 5 balls. Let's say you see 4 normal balls, 1 master balls, and then of course there are 5 balls left in the bag to be discovered. Then what you could say about the content of the bag? Then again, okay, based on this number, like one way, like one again naive way to say is, oh, there is at least 1 master ball in the worst case. But in the best case, there could, if everything else could be master balls. So in the best case, there are 6 master balls. And that's what you would do. And the numbers are between 1 and 6, which is okay. Again, is it naive? It's okay to use that as an estimation. We have no other information at all. But suppose you have some prior information about the bag. Like, okay, it's not gonna be, there shouldn't be too many master balls because again, they are expensive and you are not able to afford it. Like, it should be like almost impossible to have 6 master balls, or for the remaining 5 balls to all be master balls. Okay, so in reality, that wouldn't work. And also maybe again, just based on this sample, like if there are 5 balls in the bag, you should expect to see some normal balls, some master balls that should be in the mix. So maybe the better estimation would be to say something, oh, maybe it's between 2 and 5. If you believe that, there should be like maybe some normal ball inside the bag. There should be some master ball inside the bag. And it's fair to say that, oh, the numbers are actually 2 to 5. And here, this is a better way to estimate numbers, or to give a range of possible values. Like, given that you have some information about what the contents of the ball should look like. And the distinction between these two numbers, is that in the first way to estimate, you are 100% guaranteed to be correct, because you think of all the possible combinations or the possible arrangements, possible ways to have these balls in the bag. So you are guaranteed to be correct, which is nice. But the trade-off or the flip, the downside is that the range is pretty big, too big to be useful. On the other hand, like the number 225 that we just gave, like it's not gonna be certain. Maybe again we are unlucky, and everything else are master balls, and then you get 6, and this estimation would be incorrect. Again maybe we are lucky to get the master ball because everything else is just a normal ball. And so it could be 1, it could be 6, and we could be wrong. But here we let's say we bet like on the chance that like, it shouldn't be that extreme. And so this might have, let's say, 95% chance to be correct, for instance. Yeah, because we rule out some cases that seem unlikely to occur. But it's still, it's still non-zero probability for those cases to occur. But we rule those out. And that's why the chances are not 100%. But the good news is that the intervals are smaller. And once it's smaller, then we have a better idea of, what we should conclude about the contents of the bag, or what kind of decision would we make based on that. Like should we buy the bag and hope we get like 5 master balls, like for instance. And so in terms of philosophy, it's on you to decide which one you prefer. Do you want to be 100% sure but get numbers that are just too large, like too vary? Or you're gonna get smaller range to get a better idea of what the numbers should be in exchange for some rare chances that you could be wrong. Yes, up to you. And this is the trade-off we are going to make in the next section. And so I think the other tools are, this one is just what I just mentioned. Now it depends on, whether you want to be correct all the time or sometimes. And yeah, also just to conclude on this one, in practice, like if you can pull everything out of the bag, why not? Like, why didn't you do that in the first place? Because there are some factors, maybe cost. Like, to survey 30 people versus to survey 500,000 people, and that's on a different scales. Like, you have to hire people to go around the corner on the streets and ask every single person, and it's gonna take lots of money and also time. They are together. And maybe you start surveying now and you finish your survey in 3 years. Maybe that's what happened. And in 2 years things change and your survey doesn't matter anymore. And maybe there are too many samples. Like we talk about 500,000 people, and nobody is gonna ask every single one. Like in that case, or even in the case where there are only 100 people, and maybe it's still better to just pick 10 out of them, because maybe they live in different countries, different towns. You have to go around and ask them, and maybe some of them are too busy to answer you a short interview. Maybe that's the case. And lastly, this is interesting because like the thing is there are gonna be errors anyway. Maybe that's the final point. The reason why we don't ask every single person, well, to just pull everything out of the bag, because there are gonna be errors anyway. Maybe is it impossible to get the exact number in the first place? There could be errors from human errors. You ask them and they give you incorrect response because they misunderstood misunderstood the question, or maybe they give you the correct answer, but you misheard them and write it incorrectly, or maybe you write it correctly and someone else read your cannot read your handwriting. Mistake that. Yes, different numbers anyway. And if there are gonna be errors anyway, then why bother by making a complete number, or asking the complete or the total population to to give you the information. And so that's the concept and the reason why we have to estimate things anyway. And in the next section, we will see how we can actually do that. Like now, we're gonna use some maths